we'll do a person sliding down a hill on a piece of cardboard. So when I was a kid, there were some hills, like Louisiana is extremely flat, but there were two hills, they were called Indian Mounds at LSU. We used to take pieces of cardboard. If we got like a refrigerator or a washing machine or whatever it was that we had a giant piece of cardboard, we would take it up to the top of the hill and try to slide down the hill on the cardboard like it was a sled, because we did not have any snow ever down there. So we'll draw the hill, and then we will see to be able to calculate the acceleration of a person going down the hill on a piece of cardboard. So say we have a hill at angle theta, and then we've got a kid sitting on his cardboard on the hill. Okay, and obviously this grass is going to have a lot of friction here. And the child is going to have massive M. Okay, so if we're given mass of the child, angle of the hill, static friction of the hill, dynamic friction of the hill, we need to find part A, does the kid slide? And then B, acceleration of the kid if he does slide. So similarly to the problem before, we're going to have to do a static check to see does the kid slide. So for that one, we will use the mu s for the static check, and then we'll use mu d, dynamic friction, for acceleration. Okay, so first step is to, well, actually, let's assign some values here. Okay, so we'll say that the child weighs 40 kilograms. So that's about 80 pounds. The angle of the hill maybe is 60 degrees. The static friction between the cardboard and the hill is going to be a 0.8, and the dynamic friction is going to be 0.5. So we need to draw our free body diagram and assign our coordinate frame. Okay, so we'll simplify this to a block on a plane. So we're going to put, let's see. This one, we haven't done a slanted one yet today. So we'll say X here is going down the plane, and then Y is going perpendicular, normal force direction, normal to the plane. So we'll have all the same forces as we did before. So we've got the weight here acting down. We've got the normal force acting into the plane. And this angle between the normal force and the weight is theta. So the angle of the plane and the angle between the normal force and the weight, those are always the same angle. And then which way on here is friction going to point? Friction is going to point up the slope because it is opposing the motion. So now as far as writing equations, our plan. So we will, one, sum forces in the y direction, get normal force. Then two, from normal force, we get the friction, and we'll get static and dynamic. Do the static check. And then finally 4 is some forces in the x direction get acceleration. So if I were y'all, I'd write that down on your note card for the test as well, just this general plan of inside the write and solve equations aspect of things. So start out with some forces in the y. I'll do this one in green because our y forces are both in green. Some forces in the y direction equals 0. So some of the forces in the y is pretty much always going to be 0 unless the y is the direction of motion. The object is moving vertically because this is not coming off the plane. So pointing in that y direction, we have the normal force going in the positive y. And then we have a component of the weight that is going into the plane. So will that component of the weight be the sine or the cosine? Which one points into the plane? So the component is going to be the cosine, because if we look at this as a right triangle, we have the weight, which is going to be broken into components. We have the normal force, which is one component. And then we have a right angle. And here is theta. So the component, or basically the shadow of the weight in the vertical direction, is the side that is adjacent to the angle, which is cosine. If we were looking for this, the component of the weight that's going along the plane, here is going to be the sine. We'll use that. So this goes in the x direction, this goes in the y direction. Okay. So that's because the angle here is basically given with a vertical or along the y-axis. Okay, so we have n minus mg cosine theta. So we rearrange n equals mg cos theta. So that is the 40 kilograms times 9.81 meters per second times cosine of 60 degrees. So make sure that calculator's in degrees. And what does normal force come out to be? 196 newtons for normal force. And then we have the friction force. So static friction equals mu s. Y'all, I'm sorry, I don't know what is up with this pen today. Mu s times the normal force. And the dynamic friction equals mu d times the normal force. So we'll have here 0.8 times that 196, and then 0.5 times the 196. And static friction is always less than dynamic friction. I don't know if I told you that before, but that is always the case. So as far as what those equal, then we have 156 newtons for the static friction, and then 98 newtons for the dynamic friction. Okay, so finally, I guess not really finally, but finally for part A, we do the static check. So our static check, we need to see, is the weight of the object that's pointing down the plane enough to overcome the friction that's pushing up? So the weight component that's pointing down the plane, we had figured out right here is the sine component of the mg. So we need to see, we have static friction on one side, and we'll compare that to the weight pulling down, which is the mg sine theta. So we know the static friction is 156 newtons, and then the mg sine theta is going to be 40 times 9.81 times sine 60 degrees. this comes out to be 339.8. And so that the weight, enough weight's pulling down that it will overcome the friction. So we have a greater than sign there. And so, yes, we know that these will move. So then last step, we plug in some of the forces in X with dynamic friction and get that acceleration. So sum of the forces in the X direction equals mass times acceleration. And we will have, pointing down, the mg sine theta component, and then pointing up, we have the dynamic friction this time. So acceleration is going to equal that mg sine theta minus fd over the mass. So we've got the mg sine theta, which we had calculated above, 339.8, minus that dynamic friction, which was 98.1, and then divide by the mass, which is 40 kilograms. And then that gives us the acceleration value. So 6.04 meters per second squared equals the acceleration. And we got a positive for that. And we put our X direction positive going down the plane. So that is reasonable, that 6.04 could be the acceleration.